I have compiled a file that I'm gonna post right after this, before the review session, basically on the topics covered, so that there is no confusion. It's really everything that we've covered so far, but the lectures are 1, 2, 3, and 4 on your lecture PowerPoints that have been posted, with the caveat that lecture 4 you only go until slide 9, because that's what we managed to complete last Thursday. Okay, so that is those are the topics. Then there is also Python code, which is in your folder code on Canvas, that is related to these lectures and is assumed supplementary to whatever you have in the files, so you can work through those. Or you can work through the codes that you actually worked on during the class. Then there will be in there, so that there is no confusion, where to go for YouTube videos. They have all been posted up until last Wednesday. So there's a YouTube. I have multiple channels because I teach and record multiple classes. But you can go to the one by directly following this link or just searching. Good news is my name is unique, so the YouTube channel that you find under my name, that's me. Okay? And then homework problems that are relevant to the exam are homework sets 1 through 6. Now, we've only done 5, and we're going to assign problems for homework 6 next Monday. I think you was like, 6? Which 6? So that's going to be assigned on Monday. It's going to be due after the exam, but there are certain portions or certain problems in there that we're going to label, okay, these are the problems that are still relevant. So I think let's rethink that. Actually, we made a change yesterday, right? Thinking that is actually including everything that is relevant to the exam in homework 5. Okay, I'm going to make that correction right now. This was before the correction was made. So never mind. I'm just going to strike this. This is change real time, because I wrote this before I made the change. Okay. I will. But I wrote it before he made the change to homework, so it's like real time. And then what is allowed on the test so that there is no confusion? Scientific calculator. Graphing calculator is okay, but the simpler the calculator, the better. Not your phone or any other device. Phones will have to be moved away. Handwritten, double-sided piece of paper. You can have 2 pieces of paper. I'm not here to police number of papers and how big or small your handwriting is, okay, because that's individual. What I don't want is solved problems. So you can have syntax of the functions, you can have list all of the functions, just go through the PowerPoint slides. They can be typed, it can be handwritten. I would prefer handwritten because that way you will remember better, but it's up to you. If your handwriting is not readable, well, maybe you want to type. Okay, I'm gonna leave that to you. I suggest that you handwrite because that way you remember better. Question? You answered it. Okay, good. I'm glad when I'm responsive. That even without. And please, no solved problems. And we will pick up cheat sheets from you. We'll kind of review them and we'll return them back. You will use them on exam 2. You will just add more to it. And then on final, you will just add more to it. So by the final, you're going to have a selection of cheat sheets, right? That you are hopefully very quick looking through for the information that you need. Like a quick syntax, remembering syntax of a function or something like that. Questions? All right. So this will be posted, and there will be, I will post the practice exam. I spent some time translating it from MATLAB. So I took an actual previous exam that is representative of what's going to be on exam. It's just that all of the previous ones were in MATLAB, so I had to go and change things to Python. And I'm going to start working through those problems during the office hours / review that we're going to have after this in 2204. Okay? But I am going to post this and I am going to record this. So if you can't make it for some reason, it's going to be posted as a review class. Okay? All right. So without further ado, today we're moving on with lecture 4. So this part is not going to be on the exam, but I don't suggest that you sleep though right now, okay? Because it's going to be on the exam eventually. So we have started working with unavoidable errors in computing. And those are essentially errors related to things that they're not typos we write in. If we follow the proper syntax and we do things properly, there is still element of error in the result that is computed compared to what it should be. There are two sources of those. One is truncation error related to the mathematical formula. So mathematical formula cannot go up to infinity, and therefore we have to chop it off somewhere. In that process, we are introducing error. So simply in the example of an infinite series, I cannot go, math can go in that limit, but computers cannot. I don't have that time, so therefore I have to chop it off somewhere, and in that case I'm truncating the formula, and that introduces error. And we actually know how to quantify those, so we're typically aware of how much error is introduced. As long as it's not too big, we're good. Okay, for all of the engineering purposes, we don't have to be precisely on the point. Bridges still stand even if we have numerical errors when planning them. Okay. Now, round-off error is also there because I'm rounding off the numbers or even truncating portions of numbers because, again, I have finite memory. I cannot go infinitely and store the infinite number of digits, and that error is called round-off error. It can happen both in the case of storing actual number into a piece of memory, or when I'm actually doing computation with two numbers. At that point, there might be an error because, especially if those two numbers are very far apart. And this is one example where this is basically going to, this second number will be essentially ignored because it's way too small compared to the first. Okay. So in that case, I'm going to have errors as well. So I'm not going to review all of the class. We had some exercises at the end of it, and this is all in your materials online. We're now going to move on to figuring out, well, how is it that we store numbers on a computer so that you gain understanding on where the error is coming from. This is likely the first time you're seeing this. Let me know if otherwise. I don't think this is typically taught in high school or any previous class that you have. So this is an interesting component because it should be new. And you kind of constantly do this. You constantly rely on your Excel sheet or whatever other program to store numbers without asking yourself, okay, how is computer doing this? So here's the essential problem. My computers, they speak in on and off language. Okay? I either have electrical circuit on or off. Okay? That is 1 or 0 when we translate it to something to write down. So when I have 1 and 0, okay, I have to represent everything that I know in terms of 1 and 0 sequences. And they have to be organized in a specific way. So first, we agree on the length of these sequences, or what is the essential sort of serving of 1s and 0s that I might have. And there's 1 bit, which is 0, 1. And my word, my essential block of memory is 8 of those. Okay, so 8 bits, or 1 byte, is 1 word. You're probably very much used to bytes. Whatever you buy has memory that is evaluated in terms of number of bytes. Right? So do you know what is the memory on your computer? Do you know where to look it up? Little apple? Both. How about we go both? I think the memory on the computer is 125 gigabytes. So his hard drive can store 125 gigabytes. Okay? However, his working memory is probably 8 or 16. 8. Okay, so 8 is common. Mine is 8 as well. So 8 to 16 gigabytes are the most common laptops we now have that are relatively cheap. Okay. Now, the memory nowadays, we actually don't rely on actual machines that we carry around having all the memory. Memory could be in the cloud. Okay. which means that it's remote and we're accessing it through our wireless connection. And that is sometimes free. So on campus it's free because we all have provided wireless. It's not free. You're paying for all the fees that you're paying, but it's free. Okay. But it's unlimited in the sense that nobody is really counting how much you're using. And then you're going and accessing some memory that is on some computer elsewhere. So you don't have to carry it around. But if you're on an airplane, you can't necessarily access that. So you have to have it downloaded on your computer. The second part is the working memory. That's basically everything that computer is like storing right now. Okay? So it's basically having things in the pocket versus actually thinking about them actively. So the hard drive I can access, so it's a slow memory, and the fast memory that I'm working with right now is the working memory. So again, byte is a very common word. When I say gigabyte, it's 10 to the 9. 10 to the 9 bytes. So megabyte is 10 to the 6. So images that you typically share when you take something with your phone or camera, when you email that, it's going to have megabytes memory. And you can, maybe you pay attention to the attachment. Probably you pay attention to the attachment only when it fails. So it's above a certain limit of the memory that can be sent. Okay? So Word is the smallest 1-byte thing with 8 bits. Now, we have to agree how to store numbers, and these chunks of memory are finite. So depending on how we agree to store the numbers, I'm going to have limits in how big of a number I can store. I also have to figure out what is the type of the number I want to store. And integers are way more simpler to store than real numbers are. And in essence, I'm going to have two different ways to store them, multiple different ways, but two different kind of approaches to it. And before I access some memory that is on my drive, I actually have to know what am I reading. So when I have a sequence of 4 bytes, which is 32 bits, which is ones and zeros, they look like this. Is it what I'm reading an integer, or is what I'm reading a real number? And depending on what it is, I'm going to go and grab different portions of these 32 bits, and in different order, and I will read a bit more different things. This is the cause of a lot of confusion often, because if you don't know what's stored in the memory and you don't know the format of it, you're going to read something that is off, so what comes back to you will be garbage. Okay? So that is when we often say, oh, files are corrupted and things like those, because we have probably just misread them. So it's very important to know how to store. And typically you're not busy managing that. Okay? We're kind of highly removed, and I just want to show you how that's done on the basic level so that you understand also where the errors in computing with those numbers later come. So let's get going. First, we're going to actually figure out integers, because all these 3 classes are 3 different types of numbers that require different approaches. So let's do exercise first. Since I have to translate everything in ones and zeros, this actually introduces the problem of a base, number base we're working with. Let's say that we have coins and we only have 1 cent and 10 cents, so pennies and dimes. And what is the least number of coins of each kind that you need to have to actually arrive at 25 cents? 5 of pennies and 2 of dimes. I could go with 25 pennies, obviously, but that's not the least number of actual metal coins that I'm going to have in my hand. So if I don't want to jingle around with too many coins, I'm going to go 25. That's precisely what we agreed to do when we work in what's called decimal system. Our numbers, they go in tens. Ones, tens, hundreds, thousands. Right? When we write them down, 19 means 1 times 10 plus 9 times 1. Yes. 25 means 2 times 10 plus 5 times 1. Our base is 10, for obvious reasons. think about that. We just accept the numbering system that we are taught since we're 2-3 years of age and onward. And we accept it, and it becomes so natural that we don't ever wonder, hey, could I do this differently? So in that world of 1 base 10, I have 9 or 10 basic digits. I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the digits I'm working with. I have 10 of them. Now, what if I had only 2? My computers don't have 10 fingers. They have on switch, off switch. They have 2 fingers. So if I now had to represent all of the numbers using only 1s and 0s, what would I do? So this is my base 10. Imagine that you only have coins that are power of 2. So in the decimal system, I go by powers of 10. 1, 10, 100, 1,000, so forth. Let's just go to powers of 2. 16, 8, 1. Right? So now if I want to represent this same number, I'm going to work with the least. So I'm going to try to find the largest power of 2 that fits into 25. I'm still thinking about 25 as 25 in decimal system because we got to start from somewhere. But 16 is the largest power of 2 that fits into it. So I can have one of those. I can't have 2. And in a system that can only have digits 0 and 1, I will never go to 2 of anything because that increases the power that I'm using. If I can fit 2 times 16, I can fit 32, and that's my next power of 2. Okay. So I'm not going to do that. I'm just going to use 0s and 1s. So basically, I have 1 times 16. Then what's left? 25 minus 16 is 8. It's 9. So my largest power that fits into that reminder is 8. So I have 16 plus 8, and then I'm left with 1, which is a power, the 0th power of 2. Are we following? So those are my digits that I'm going to work with. And I'm going to order, and I'm going to place 0s where I don't have the power. So it's 1 times 16 plus 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. That is 1, 1, 0, 0, 1 in base 2. And that's what a computer will do. These are now my bits, 0, 1. I can have 0, 1 on and off. Okay? So computer has only 2 fingers, aka on and off switch. Did this just blow your mind? No? Has anybody seen it before? Huh? Maybe? All right. That's how we're talking or translating integers to computer memory. Now, again, we use decimal system every day. Don't think about it. And in that system, I have 0 through 9. Computers use binary, which is base 2. Digits allowed are 0 and 1. Now, doesn't really matter to computer or to math. I could have base 3. So I could ask you to translate the number in base 3. Then I would work with powers of 3, which are 1, 3, 9, 27, and so forth. Or powers of 4, or powers of 7, or powers of 16. It's just that in powers of 16, I would run out of digits as I know them. So I would have to start with A, B, C, D's or something in place of digits. And not something that's actually used. That's hexadecimal system. And you will see that sometimes actually these numbers are translated. There's a simple rule that translates them to hexadecimals, and then you're going to see A, B, zeros, A, B, C's, D's, and so forth. Okay. And you can see that occasionally in movies if you but if you don't know what you're looking at, you might not know. So again, base, as far as math, is either one could work, but we naturally use decimal systems. Computers naturally use binary. Okay. Now, just for the fun of it, okay, technically, if I was just representing things in base 2. If I had 0.75, okay, in decimal system, after I place a 0, I still continue with powers of 10. This is 7 times 10 to the minus 1 plus 5 times 10 to the minus 2, correct? So I'm going on with powers of 10 all along. And the way I shift this point is by multiplying or by dividing by 10. I could do the same with 2. So 0.75 is 0.5 plus 0.25. It's 1 over 2 plus 1 over 4. It's 1 times 2 to the minus 1 plus 1 times 2 to the minus 2. Are you still with me? So in binary system, this same number would be 0.11 in base 2. Are you still with me? No. So the same number, 0.75, is 0.5 plus 0.25, which is 1/2 plus 1/4. Those are powers of 2, just negative powers. Just like I'm working with negative powers of 10. 7 times 10 to the minus 1 plus 5 times 10 to the minus 2. So I could translate that number to base 2 that works with powers of 2. Well, I'm going to move on from this example. But yes?
For the second example, you have 32. You have 2 times 16.
So then I would actually have 32, one more, so I would have 1, 0, 0, 0, 0, 0 in base 2. Just like if you had, instead of hundreds, you had 1,000. Right? 1,000 is 1, 0, 0, 0. So that's 1 times 10 to the 3 plus 0 times everything else.
So then you're saying you have a huge number.
You would have to have huge number of digits, yes. And that's what poses limits. So I might actually have what's called memory overflow if I'm asking to store bigger number than I have digits. Thank you for that introduction. So now I actually need to put that into a computer. Okay? So I can choose to store things, typically integers, using one word, which is 8-bit number, 2 words, which is 2 bytes, so that's 16 bits, or 32 bits. And because of that, I have a limit on the size of the number I'm storing. So let's see what's the largest. So back to this number. If I was actually storing this in memory, I go in chunks of 8. So I wouldn't use only 5 bits, I would use 8 bits to store this, and have zeros in front where I don't have anything. So if I would just fill this in with zeros, right? So if I go larger number, I need sort of more bits. So in this case, here's one such larger number, which is using all 8 bits. Okay? So 173, the largest power of 2 I can fit is 128, then plus 32, plus 8, plus 4, plus 1. You can check that by hand, which is 2 to the 7 plus 2 to the 5 plus 2 to the 3 plus 2 to the 2 plus 2 to the 0. I have zeros in between. So I go, this is my 0th power. First power is 1, a 0. Second power, third power of 2, fourth power, fifth power, sixth power, seventh power. Do we see ones and zeros? You get these real soon, right? The ones and zeros, we're not very well equipped to differentiate where all of those are. So are we clear where zeros are here? Because there's like a 0 times 2 to the 1 here. I have to order them. Okay. Now I could keep going. So most computers will reserve 16 or 32 bits per integer. And now I'm wondering, what is the largest number I could fit into that memory? So let's say that I had 16 bits. Okay. I could, these powers, they start from 0th power. So 0 to 15, okay? And the largest number to fit in there will have 1s all along, yes? So 1 times 2 to the 15 plus 1 times 2 to the 14 all the way down to 1. That happens to be 2 to the 16 minus 1, which is 65,535. So if I reserved, and I have to know what is the memory I'm reserving ahead of storing something into that memory. If I was reserving only 16 bits per every integer, the largest integer I could store is around 65,000. Anything bigger, I have numerical errors. And I have to be aware of it. Where can you hit a problem like that? Let's say that you're designing something and you reserve numbers that are only going and they refer to something in your system. I don't know, let's for the sake of it, just think that we're like drilling and we're constantly drilling wells that are 10,000 feet in total depth, both horizontal and let's say that we suddenly, so we're like, okay, for the number of feet here, I can go with 16 integers because I'm mostly under 65,000. And then one day technology moves forward and we go above that. So the entire system that we built on storing things that we're using only, or storing depths that we're only using numbers that can be below 65,000, I suddenly introduce error in the system. So you don't have to know all of the details of how things are stored until you do. Okay? So typically with technological advances, you will go above little by little, little by little, little by little, and somewhere there's a threshold. Right? You go above what was actually doable with the system that was put in place 10 years ago. Okay? So then you have to kind of revamp and move on. So this is why this is a motivation to also introduce you to problems of this sort. I had that with a friend of mine who was working in Texas Advanced Computing Center, and they were scaling things up to work with multiple cores. And most of the times, and they are constantly pushing. TAC here at Texas is one of the bigger parallel machines in universities anywhere. And they're constantly trying to push things to bigger and bigger and bigger. There's competition going on. Right? So for longest time, they never had more than 50,000 cores. And they go and they built a system that had 80,000 at the time. And they were trying to push to use all of them. And all of the integers that we're using were 16-bit integers before that, when dividing the jobs among machines. So the machines had only labels that went up to 65,000, and they were trying to use 80,000. And the computers, they're sneaky. They're not going to always report an error. They're just going to give you some garbage back. So it took them 2 weeks to realize that the number type that they're using is too small for the number of machines they now have because they went above this threshold. Okay? So these errors are real. Okay? They're fine until they're not fine, and then you have to know. All right. So this is my memory. Okay. So if I had this 173, there is one more thing I have to figure out. Do I want to use negative numbers at all or not? So if I want to use negative numbers, then one of these bits has to be stored for signs. So that kind of limits the magnitude of the numbers I can do. It divides them by 2, essentially. So then I have to, and I have to know that too. Is my integer that I'm storing signed or not signed? Signed or unsigned? Okay. So if I do use for signed, then this first one, minus 173, okay, would have this 10110101 would be here. The rest are 0, and then the one reserved for sign is minus. Okay. So again, this is where my absolute value of the number is right here. What I don't have, I fill in with zeros, and then I have one digit at the front that is reserved for the sign. Okay. So it's bookkeeping, quite a bit of bookkeeping. And there's also agreed rules of how this is done. This did not develop overnight. So computer scientists had to figure out, okay, this is how we're going to do this, and then everybody follows this system. So if you were actually trying to do 25 in a computer, okay, can you take a piece of paper and write it down for yourself? Reserve 8 bits, and in the second problem reserve 16 bits. Okay? And just write it down. How does it look like in memory? If my number 25, which I have what it is right there. So you have to fill in a certain number of zeros. And this is like your question in exam 2. Not exam 1. But this is a typical one. How does such and such number look in the memory? Okay. So just put 8 little boxes as 16 little boxes. And just show how it looks like with all of the zeros filled in. Yes?
Okay, so for like the first number, the sign,
Mhm.
goes to 0,
Positive.
okay, so 1 means negative.
Yes. And that's again, we have to agree on that. Okay? It could go either way, but you have to have a rule. Right? So again, put a bunch of boxes and put 25, and then you can play with minus 25, would just have change in that first bit. But I have to know that that's supposed to be interpreted as a sign as opposed to the magnitude of the number. Okay? Any questions? Yeah.
When you said that the sign with 0 being positive and 1 being negative, we have to agree.
I have to know that I'm storing a signed integer versus unsigned. Okay? Otherwise, that 1 can be interpreted as a sign or it can be interpreted as a magnitude. Okay. Mm-hmm.
Is it 1 at the very front positive?
No, 1 is a negative. Yeah. As in, I have a minus there. Okay. So again, if I had 25, here numbers would be 1, 0, 0, 1, 1. The rest would be zeros, okay, all the way, if it was positive.
16?
Yeah, if it's 16-bit, otherwise all the way to 8-bit. Okay?
So if you have something that fills in all of the boxes,
Yeah, that's what computer does.
would you not have a sign then? It would just all be
Yeah, then you can decide that unsigned integers, you're going to store, if you have a 16-bit, you're going to have numbers from 0 to 65535, right? But if you, in the same chunk of memory, want to store numbers that could be both positive and negative, then it's going to be from minus half of that to plus half of that. Okay? If I reserve 1 here, then the magnitude of this number is twice less than the one that I could fit before.
So if it's 8-bit, that 1 does like for the other one?
Yes, if it's 8-bit, it's either from 0 to 255 for unsigned, or from minus 127 to 127. With the one more little detail. Okay? So, if I had 8-bit number, just a moment. So, technically the range of integers, that was just a question right here, I already had on the slides, is from minus 127 to 127. In that system though, if I'm reserving that first bit for a sign, I could technically have plus 0 and minus 0. Right? If I reserve first one for the sign, I could have sign both ways, and I could have zeros everywhere. So I could technically have a positive 0 and a negative 0. Mathematically, positive 0 and negative 0 are both 0. Well, computer doesn't know that. You just tell computer what to do. Computer doesn't do math. You tell it to do math. Okay? So there's actually, so one of those that's kind of based in already a limited range of numbers. So there's an agreement that one of these zeros is going to be mapped to minus 128. Okay? Just to expand the range a little bit and not base the range and store 0 twice. Again, that's just a rule that is agreed upon. So if you will, there's a little if loop in there asking, hey, is this a negative 0? If it's a negative 0, I'm going to map it to minus 128. So technically, the range of integers that is stored is really from minus 128 to 127. I can do the same rule for 16 bits. It's just that my range is going to expand a little, or for 32 bits, it's going to expand even more. And these days, integers are pushing to 64 bits too. So I can keep going. I just have to agree what is the size of my integer going to be so that I can read the memory correctly. Questions? So again, unsigned 8-bit integers has range from 0 to 255. Okay? And again, I can do the similar calculation for 16-bit and 32-bit integers. Okay? So now if I go to floating point values, okay, I'm going to go into a little bit of more written details later, but I'm just going to give you a high overview right now. Technically, now I have numbers that if I have to first figure out what is the notation for my number going to be. And what's agreed upon is to use scientific notation. Okay? So normally if I had 37.5, I would actually put that to a number that is larger than 1, 3.75 times 10 to a power. And similar thing I would have for something that is less than 1. I would, in this particular case, this particular example, say, hey, it's minus 8.125 times 10 to the minus 4. So in this notation, okay, I would have to also convert this to a binary format, but I'm not going to bother you with that part yet. So technically, this actually goes also into powers of 2. And then I'm left with this, what we're going to call mantissa. Essentially, I need to store this part and exponent, both of them separately. I have two numbers. If I know that this is the representation of my number, okay, you can just focus now on the decimal system. Conceptually, it's the same. I have a mantissa and exponent to store. Now, how do I do that? I have certain number of bytes that I'm going to reserve for storing a floating point integer. Floating point is real number in computer speak. So I do this real number. So then in those number of bits, I have to simply say, okay, this chunk is going to be reserved for this part, this chunk is going to be reserved for that part, right? So the way it's done is that if I have 32 bits to do that, I'm going to save 24 bits for mantissa P and 8 bits for exponent T. Okay. And in the what's called double precision, I'm going to use 64 bits. And again, agreement is to use 53 bits for mantissa and 11 for exponent. Yes? It's actually, yeah, it is done in base 2. So you go to scientific notation of a number in base 2, actually. Okay. And then in that base, I'm not going to go now into super detail, but basically, if you go into something larger than 1 and you're in base 2 for mantissa, you're always going to have 1, so you don't store that 1, you store everything else. Just to reduce the storage. Let it go. You need something for the mantissa part and exponent part. Just focus on that. Okay. So basically, again, I have finite space for either. And that creates issues when storing numbers. I'm not going to be able to store numbers as large as I'd like to, right? and even as small as I like. Because when I go small in a scientific notation, my exponent increases in a negative way. So I'm going to go 10 to the minus 400 or 10 to the minus 1000, right? At some point, there's a limit to that exponent that I can store. So if I cannot do 10 to the minus 1000, that means that there are certain small numbers I can't store. And if I look at the positive exponent, there are certain large numbers that I can't do. Okay? So I have what we call underflow when I go below what I can store, and overflow when I go above in magnitude of what we can store. So we have limited range. It gets even better. Because when I look at the scientific notation, let's assume that this mantissa, okay, can somehow store just 4 digits. Okay, just 4 of them. So the only thing I can store is 8125, and if I actually had 8.1256, that 6 I wouldn't be able to store. Yes? Because I don't have the space for it. That means that I'm creating gaps in between the numbers I can store. I can store 8.125, and the next one I can store is 8.126. And everything in between that has more digits, like 8.1251, I can't store. Or 8.1252, I can't store. Right? All of those in between, right? I have a gap. And that gap is of the width of the 10 to the minus 3, right? Because of the limited, yes? So there's all this, due to the chopping, you effectively cannot store certain numbers accurately. You're going to make a mistake. You're going to approximate them. Right? So they're all going to be mapped to the rounded off version of the number. And you're rounding off to however many digits you can store. So do you conceptualize this without writing it down? I'm going to actually do an exercise of kind of writing it down next time. But I just want to first gloss over it conceptually. That first thing first, very large numbers in absolute value I can't do. Very small numbers in absolute value I can't do because of the limits on the exponent. And then in these limits on the mantissa, right, there's certain little gaps that I'm going to have in my real number continuous line. So I have to be aware of that because that's what's causing, it can pile up numerical error when I'm storing the data. So this is actually, I'm going to ask you for your exam too to simply have this on your cheat sheet just to be aware of it. Okay? So technically for integer, this is Fortran and MATLAB, and Python actually borrows the same. Okay? So for integers, I'm going from minus 32,000 to plus 32,000 if they're signed. Okay? In single precision numbers, so this is my numbers, so this is sort of on a line. This is sort of like numbers close to 0 that are in between 0 and that minimum number, okay, that I can store. Okay, these are the ones I cannot store. I can do 0, but something that is like 10 to the minus 1000 I cannot do. Okay, but I can do actually the smallest in double precision. The smallest number I can do is 2.23 times 10 to the minus 308. Okay, obviously I'm not going to ask you to memorize this, but if you look it up, you can actually tell me, hey, is this number possible to store? Is this number impossible to store accurately? Okay. So whenever we actually attempt to store something that is smaller, we're getting an error that is called underflow. Computer will do something. Most of the time it's just going to zero it out, which is a good outcome, but it could actually just store some garbage, which is a bad outcome if it doesn't tell us. And then overflow, if you go in absolute value much larger, you have so-called overflow. Most of the time, computer will map it to something called infinity, INF. Occasionally not a number if you're dividing by 0. So what is it going to do? It kind of depends on the system and the program and the computer. computing environment, it doesn't always tell you, it just assigns things and proceeds. The computers are never really busy asking, like, why are you doing this? Unless somebody programmed it to ask, why are you doing this? So every time you actually have error printed on your screen, somebody programmed it to report the error. Otherwise, it will just proceed. And garbage in, garbage out. So in that sense, however fancy your algorithm, if you provided it with data that goes into overflow or underflow, good luck. So let's actually see if we have comprehended any of this. So let's say that I have a 16-bit integer. Can I store 4 million in that? Can I do 30? Can I do it in a 32-bit integer? Yes. What is the largest 32-bit number if they're positive? It's actually going to be, so let me give you a useful formula. So in 32-bit positive ones, it's 2 to the 31 plus 2 to the 30 plus all the way down plus 2 plus 1. This is placing ones in all of the bits. This formula is actually, it's really equal to 2 to the 32 minus 1. So one more up and then minus 1. Formula for math is actually x to the n plus x to the n minus 1 plus all the way down in integer exponents is 1 up x to the n plus 1 minus 1 divided by x minus 1. In case of 2, I'm dividing by 1, so I don't care. This is just a formula. You can actually see it. If you multiply, you'll see that it's true. So what is it? Can somebody compute this?
429, 496, 7295.
So how many of them? Is 4 million smaller than that or larger than that?
Smaller.
Smaller. So I can do it in the 30. So this is how I check. Questions?
Why is it 2 to the 31?
So this is me imagining 32 bins
Because computer
in a
language.
32-bit number, filling them with ones. Okay? That's equivalent then to 2 to the 1 times 2 to the 31 plus 1 times 2 to the 30, okay? All the way down. All of these are ones. This is unsigned. Okay, so at 3 o'clock, I'll be in 2204, and I'll post review, and we're going to work on problems that are related to the exam.